Hello and welcome back. Today we are going to look at the notion of homeomorphism. So we have been looking at the notion of continuity. Now, homeomorphism is a function that's continuous. Its inverse is also continuous. So let M and N be metric spaces, and we have a function f that goes from M to N. So we say f is homeomorphic. So f is homeomorphic if the following three conditions are satisfied. F from M to N is a bijection. That means it is an invertible function. Secondly, the function is continuous. N is continuous. And the inverse is also continuous. Inverse goes from N to M is also continuous. So if these three conditions are satisfied, then we say F is a homeomorphism. And if there is a homeomorphism between M and N, there exists a function that satisfies these three properties, then we say M and N are homeomorphic. And it is actually important to check the last property as well, because it might be tempting to find a continuous function that is bijective and say it is a homeomorphism, because sometimes the inverse may not be continuous, so do make sure to check that. We will look at some examples where the last property causes some trouble. So let's have a look at some of those. The first example is as follows. Now consider a function, let's just say 0, let's look at the closed interval, like half closed interval, 0, 1. So this means part of the real line where 0 is included, but 1 isn't included. So this line. And with the metric given by the standard metric, which is the absolute value, where d of x comma y is the standard absolute value of the difference between x and y. So this is our one metric space. Now consider another metric space, a circle with d that's inherited from R2. So what it means is that you think of a circle as the circle sitting inside R2, a unit circle sitting inside R2. And if you want to compute distance between any 2 points, say A and B here, you just draw a straight line in R2, and this length is the distance between these 2 points. So that's what it means. The metric is given by that. So now let us look at a function f that goes from this half open interval to the circle. Say x goes to cosine of 2 pi x, sine of 2 pi x. You will see that this function is a continuous function. Now, I'm not proving that this function is continuous because there are more powerful ways of proving functions are continuous in the future, and I will show you all those techniques. For now, you can check that this function is actually continuous using epsilon delta definition. But the function is invertible, but the inverse is not continuous. And this is just a vague example because I haven't told you why the function is continuous and why the inverse isn't continuous and why it isn't a homeomorphism. In fact, it will turn out that there does not exist any homeomorphism between this and this, like these two metric spaces, because it might be the case that, yes, we came up with a function and this function failed to be a homeomorphism, but maybe there's some other function that's going to be a homeomorphism. Turns out that's not going to happen, that these two are not homeomorphic to one another. Another non-example would be as follows. Now consider R with the discrete metric space. So if you don't remember, Discrete metric is the metric in which we say the distance between any two points is 1 if the points are different, and the distance between a point with itself is 0. And let's look at the metric space R, the same set, but with different distance function, the standard one. And by standard, I mean distance between 2 points A and B is given by the absolute value of the difference between A and B. Now we know any function from the discrete metric space, any set with a discrete metric, to any other function is continuous. So in particular, if you choose the identity function, identity at the level of set, because 1 goes to 1, 2 goes to 2, pi goes to pi, and root 3 goes to root 3, like the identity function, is going to be continuous, because identity is continuous, because it goes from a metric space, a discrete metric space, to any other metric space is continuous. Identity is invertible, it is bijective, because the inverse is also the identity, but the inverse isn't continuous. The identity that goes from R, D standard to R, D discrete is not continuous. And I will show you why it isn't continuous. You can pause the video now and then try and prove that it isn't continuous. In order to be continuous, we need to look at the epsilon delta definition. So let epsilon equals 0.5. Then what we need to show is that, let's pick a point, say A. We will show that this function is not continuous at A. If epsilon equals 0.5, we need to find a positive number, delta, such that the distance standard of x, A is less than delta, implies the discrete metric space of the function applied to x and A is the identity function x, A is less than epsilon, is less than 0.5. And what we are trying to prove is that we can't find any delta. There is no delta that makes this true. Now, in the discrete metric space, the distance is always 0 or 1. If it's less than 1, then it's 0. That means x is equal to A. Now, in the standard metric, if you choose any positive delta, it will always happen that there is some x that's not equal to A, but that's really close to A. Because you could choose delta equals 0.001, then A plus 0.0001 will be in that neighborhood. So no matter how small delta we choose, as long as it's positive, and we want it to be positive, there will be x other than A satisfying the standard distance between x and A is less than delta. And then this in particular is not going to imply x equals A, because there will be some other x, and this does not imply x equals A. So therefore, the inverse is not continuous. So this identity function from the standard metric to discrete metric is not a homeomorphism. In fact, the only continuous function from the real number with the standard metric to reals with discrete metric are constant functions. And we will prove that in the future. And this property is known as being a connected space. We say that R with the standard metric is a connected metric space. That's a lot of non-examples. How about some examples? Well, now if you look at a metric space with some metric, if you have a map to the same metric space with the same metric, then identity function is going to be a homeomorphism, because it's going to be a continuous function. You can choose delta equals epsilon in delta epsilon definition. And the inverse will be the identity itself, and it's also going to be continuous. The function is going to be bijective, and this is a homeomorphism. If you look at, let's look at another example. If you look at a circle, say with the metric that's given by thinking of this circle as sitting inside R2 and it being a unit circle and the distance between 2 points is a distance in R2. And same thing as the square, maybe a little bit bigger square. I don't know how bigger. The metric given by thinking of this square, depending on how big of the square you choose, sitting in R2. Then you can find a continuous function that just stretches this circle into the square, like so. And this function, I'm just going to write f from circle to square, is going to be a homeomorphism. Is a homeomorphism. So we say circle and the square are homeomorphic. I will give you one last example. It's a famous one. Say a donut. Say with the metric function given by thinking of donut as living in R3, our universe. Physicist, please. Yeah. Try to stay quiet. So our universe, if we think of it as a three-dimensional universe, then donut, we can think of it as living in R3, and we can inherit the metric from R3. And the same thing with the coffee cup, with the metric given in R3. This is a homeomorphism. So what you need to do is, it's just like the circle and the square case. You start with a donut, and you keep this whole, and then you look at this part and just make it bigger, and then punch and try to make a hole in it. But not a hole, like you make it punch and just make it like the coffee cup shaped. So what you do is you get something like this. And the actual hole in the middle just becomes this hole here. And this is a homeomorphism. Okay, those are some examples and non-examples of homeomorphisms. Hope you enjoyed this video. I look forward to seeing you in the future. Bye.